Hello everyone. So today we will study about conjugate beam method. By this method we have to determine displacement of the structure, and conjugate beam method is also one of the geometric method by which we can determine displacement of the structure. So here also we have two theorem 1 and theorem 2. So I will explain you what is theorem 1 and theorem 2. So this is theorem 1. It states that the shear at any point in the conjugate beam is equal to the slope at the corresponding point in the real beam. So what we have to do here, they will give you real beam, and that real beam we have to convert it into a conjugate beam method, a conjugate beam, and at any point shear in the conjugate beam will be equal to slope at that particular point in the real beam. Okay, so in order to find slope in the real beam, you have to find shear in the conjugate beam. Is that okay? So now we will see how to find deflection. This is about rotation. The theorem 1 deals with the rotation and theorem 2 deals with the deflection of the beam. So by theorem 2 we can easily find deflection by using conjugate beam method. So the statement here is moment at any point in the conjugate beam is equal to the deflection at the corresponding point in the real beam. So I told you they will give you real beam, and that real beam you have to convert it into a conjugate beam, and moment in the conjugate beam is equal to deflection in the real beam at that particular point. Okay. Now class, here if I take y and this y is deflection in the beam. Okay, when I derivate this y with respect to x, so it will be dy by dx, which will be equal to rotation or slope. Okay, so when you derivate y term with respect to x, you will get slope or rotation, and again when you derivate this with respect to x, so you will get here d square y by dx square, which is nothing but a curvature. So you know from the flexural formula, m by ei is equal to d square y by dx square. So this d square y by dx square is nothing but a curvature. Okay, so when you derivate y, you will get rotation. When you derivate rotation, you will get curvature. So in this way, if we are going in this direction, we are derivating in this direction, okay. So you are getting from deflection rotation, from rotation curvature. And if we go in a reverse direction, it will be integration. When we are going in this direction, we have to derivate. Derivation of deflection is rotation, derivation of rotation is curvature. When you are going in a reverse direction to this derivation, so the integration of curvature will give you rotation, and integration of rotation will give you deflection. Okay. Now see here we have two variables, two important variables. One is called kinematics variable and other is called static variables. Kinematics variable means the displacement content. Okay, displacement content means what are the various displacement content in the structure. So we have deflection, we have slope and curvature. So these are kinematics variables or kinematics variables. Static variables means the internal forces developed or the forces. So we have load intensity, external load, which may be UDL, okay. We have shear force and bending moment. So what we have to see here, derivation of deflection is slope, derivation of slope will give you curvature. In the same way, when you see the static variable, derivation of moment is equal to shear force, okay, and derivation of shear force with respect to x is nothing but load intensity. Okay, So derivation of moment with respect to x will give shear force, and derivation of shear force with respect to x will give you load intensity. Now I told you we have to convert a real beam into a conjugate beam, and how shall we convert it? Now see here, first we have to take a beam, a simple beam. Okay, I will take a simple example, W L by 2, and bending moment diagram will be in this way, W L by 4. Okay, we have to convert this bending moment diagram into curvature diagram. We just have to divide it by EI. So this height is WL by 4 EI. Okay, now it is curvature diagram. So what we have to do here, we have to convert this curvature diagram into a loading diagram. Okay, we have to convert this curvature diagram into a loading diagram, and that will be your load intensity. Curvature diagram will act as load intensity. Okay, now see here, shear force will be equal to slope, and bending moment will be equal to deflection. So this curvature diagram we are equating it to load intensity. Okay, so this curvature diagram will be just like a load intensity. We have to take this as a load, and shear force in this beam, in this conjugate beam, will be equal to slope in the real beam, and bending moment in this conjugate beam will be equal to deflection in the real beam. We just have to see what boundary condition we have to provide. We will see, but first we have to convert it into a conjugate beam which can be done by having curvature diagram and applying some boundary condition. We will see what are the various boundary condition in this. Now class, here we will study boundary condition. Means we have to see the support in the real beam and what will happen to that support in the conjugate beam. Okay, so here we have a simply supported end or simply support or a roller. Okay, so at simply support, theta is not equal to 0. Everyone knows theta rotation is not equal to 0, but deflection is equal to 0. Okay, so same we have by using same concept we have to apply boundary condition here. Slope moment is no, shear force in the conjugate beam is equal to slope in the real beam. So here shear force should not be equal to 0, because shear force is equal to rotation in the real beam, and moment should be equal to 0. Moment in the conjugate beam is equal to deflection in the real beam. Okay, so if we provide the same support, simply supported in the real beam is equal to simply supported in the conjugate beam. Here shear force is not equal to 0, but whereas bending moment is equal to 0. So even you can if they give you roller support in the real beam, which will be equal to roller support in conjugate beam. So in at roller support also, shear force is not equal to 0, but bending moment is equal to 0. So next we have hinge support or hinge end. At hinge end, theta is not equal to 0. Okay, but bending moment is equal to 0. So here also in conjugate beam we will have hinge support where shear force is not equal to 0, but bending moment is equal to 0. Okay, so then we have a fixed end. At fixed end, theta is equal to 0 and delta is also equals to 0. Which support we have to provide here, so that shear force is equal to 0 as well as bending moment is equal to 0. So fixed support in the real beam will be equal to free end in the conjugate beam. Why it is free end here? Because at free end shear force is equal to 0 and even bending moment is also equal to 0. So we have satisfied the boundary condition. Shear force is equal to rotation in the real beam and this moment in the conjugate beam is equal to deflection in the real beam. Okay, so we have to satisfy this condition. When we provide free end here, shear force is equal to 0 and bending moment is equal to 0. If you are providing fixed end, moment is not equal to 0 here and shear force is also not equal to 0. So we are not satisfying this condition. Okay, so we have to provide such support so that we are providing or we are satisfying this condition. Okay, fourth, free end. Free end, this is real beam and here we have a conjugate beam. Free end, it's a free end. Okay, so at free end, theta slope is not equal to 0 and even this delta is not equal to 0. So what we have to provide in conjugate beam? So free end in a real beam will be equal to fixed end in conjugate beam. Okay, so at fixed end, shear force is not equal to 0 and bending moment also not equal to 0. Then we have a intermediate support. Intermediate support, or you can say interior support, which is common in case of continuous beam. Intermediate support, like this support is here, which may be roller or hinge. At intermediate support, slope is not equal to 0. Okay, but delta deflection is equal to 0. So what we have to provide in conjugate beam? Intermediate support in the real beam will be equal to internal hinge in conjugate beam. Okay, so at internal hinge, shear force will not be equal to 0, but bending moment, you see this condition, bending moment will be equal to 0. Then we have this is real beam, conjugate beam. Then we have internal hinge in the real beam. At internal hinge, theta is not equal to 0 and delta also is not equal to 0. Okay, so internal hinge in the real beam will be equal to intermediate support in the conjugate beam. So at intermediate support, shear force is not equal to 0 and even bending moment is not equal to 0. So these are the boundary conditions that we have to apply when we are converting a real beam into a conjugate beam.